Hello, today we'll be speaking about nuclear fusion. Most importantly, we'll be addressing two main types of questions. What is nuclear fusion? And also, how can we use it to generate usable energy? Because in the future, energy's main resource, which is fossil fuels, will eventually disappear. So we need to find a solution. First of all, what is nuclear fusion as a reaction? Let's make it simple for you guys. If you take two light elements and combine them, it will make a heavier element. Now, if we have a look at a more detailed explanation, the best two elements for a fusion, nuclear fusion to occur, are deuterium and tritium. These are two isotopes of hydrogen that we can use. Basically, when these two isotopes fuse, they create helium, neutron, and most importantly, they yield energy.
But why do we use deuterium and tritium instead of other elements to create nuclear fusion? It's fairly simple. It's because these two will react more efficiently. That's because there's less repulsion between them, as there's only one proton in each one, instead of more and heavier elements. Also, when they react, they will release more energy compared to other reactions such as the hydrogen and hydrogen one that occurs in the sun. Lastly, they will reach a self-sustaining temperature more easily, which means that at some point the energy from one reaction will be able to cause one more reaction after it, and so on.
The natural. So, as you see, deuterium plus tritium creates a reaction, a fusion. Then fusion release energy, helium and neutron.
But where does this energy come from? Well, where it comes from what's called the binding energy of elements. That's the energy that's needed to separate all parts of an element, but also the energy that's released when they all come together. So here, deuterium and tritium come together to form helium. When these subatomic particles come together, they release binding energy. But where does this binding energy come from still? Well, we notice that the mass of helium is lesser than the mass of deuterium and tritium. Why is that? It's because this difference in mass was converted into energy that became the binding energy of the helium, and that was otherwise released as energy through heat, light, and kinetic energy of the neutron. Still, to release all this energy, there are certain requirements that must be met. The first is being able to fuse deuterium and tritium. But that's not always possible because both are positively charged ions, which means that they repel each other.
This repulsion, meaning that they can't attract to each other, is called the Coulomb barrier. So here, for example, we have two particles with the same charge, in this case positive. The requirement is that it needs extremely high temperatures to function or work properly.
At that point, they reach the state of matter called plasma.
But what is plasma state? That is a very simple question to explain. Plasma state is the fourth state of matter after solid, liquid, and gas. It is basically ionized gas, meaning that there was so much energy put into it that it freed electrons, allowing, in this atom, electrons and positively charged ions to coexist together. In the Earth in which we live in, plasma is very rare, which means it is not common at all. However, in the universe around us, plasma state is the most common state that exists. It also has a very high kinetic energy.
After reaching the state of plasma, the other requirement that we need in order to achieve nuclear fusion is to confine the plasma. What that will do is it will stop the energy released from escaping, and instead it will go into fueling other nuclear reactions. The energy could escape through heat, through conduction, radiation, or convection.
But why can't we sustain nuclear energy? Well, the thing is, we can create plasma to confine and therefore create nuclear energy. We have done that before, but the amount of energy used to create this nuclear fusion is always bigger than the amount of energy yielded from the reaction, which makes it a waste of time. That's why we are trying to lower the cost of energy and find a way that would allow us to create more energy than the energy used before the reaction.
So, there's another way of confining nuclear fusion, and it's called inertial confinement fusion. As you can see here, the laser gets in a chamber, and then it activates the fuel. The fuel is made out of deuterium and tritium.
The energy released from inertial confinement fusion is greater than the energy used to cause the fusion. So why can't we use this technique to generate energy from the reaction? Well, it's because all of the energy is released in a single burst, and because of that, it's not possible to get enough of it to make more energy than what was used to cause the reaction to occur.
After the long lapse trying to make this kind of reaction work, it is crucial for us to stop for once again and try to understand the tremendous change that would occur in case we ever get to make this reaction happen. So first of all, on the sanctuary level, we will be able to stop toxic gases from spreading in our air, and would also be able to fight climate change. In addition to that, like on the economical level, we'll be able to produce our own fuel and therefore have more fortunes and still stop pollutions. And finally, this kind of fuel will allow us to go to Mars in 1 month, which would allow us to make new explorations on other planets.
Knowing that nuclear fusion has been achieved before, what were some ways that it was done? One way that we will look at is magnetic confinement. This technique uses an electromagnetic field to confine the plasma, because we know that the plasma is made of positive ions and electrons. So these charged particles are affected by the magnetic field. This is because of what's called the Lorentz force that we see here. These particles spin about the lines of the magnetic field, thus causing them to stay in one space.